Hi, in this set of lectures we will see what is called as the revised simplex method. Why do we need a revision in a method that we can already use to solve our linear programming problems? Well, let's take a look. If we go back to how we solve our LP problems using simplex method, we have to essentially maintain a state of all the calculations from our past tabular that we calculated. That means the next tabular that you work on depends upon the values that you have in the previous tabular. Now the problems that we've dealt with have maybe 3 or 4 variables, so it doesn't get that challenging, but in real world problems the number of variables could be in hundreds or even thousands. Now if you realize that the amount of calculations and the amount of storage in memory that is needed to solve the entire simplex would be computationally very expensive. We will now look at a method that makes it possible to maintain only the state of the problem that is important and then recycle rest of the memory. So before we actually look into the revised simplex method and what are the steps involved in it, let's define what is an inverse of a matrix. For a square matrix, if we represent a raised to the power minus 1 as the inverse of a matrix A, then a raised to a minus 1 multiplied by a gives us an identity matrix. An example of an identity matrix is shown on the screen here, and if we think about it, it is something similar to our canonical form. One more thing that we want to keep in mind is that if A is an identity matrix, then the A inverse is also the identity matrix. The inverse of an identity matrix is the matrix itself. We'll pick up an example to learn the revised simplex method. So consider ALP. We are asked to maximize z is equal to 9x1 plus 7x2. The constraints are 10x1 plus 5x2 less than equal to 50, 6x1 plus 6x2 is less than equal to 36, 4.5x1 plus 18x2 is less than equal to 81. And here is the graphical solution. We have done this earlier. We plot the 3 constraints, find the basic feasible region. One of the corner points in the feasible region will be the solution. For this particular problem, the answer is that x1 is equal to 4 and x2 is equal to 2, and the maximum value that we get is z is equal to 50. Now let's look at what are the steps that we will be following for revised simplex algorithm. So the first thing we'll do is we'll define and identify the original column vectors Pn. What do we mean by Pn? We'll see it as we perform our steps. We will also define the coefficients matrix Cn of the objective row. Next, we will calculate the new column vector Pn prime for the non-basic variables and xb, where xb is the right-hand side column vector. Once we do that, we will then identify the new basic variable. Then we will find the exiting row. Again, this method is also very similar to what we've done earlier in our simplex method. And then we will repeat step 2, 3, 4 until no more new basic variables can be identified. At an abstract level, the method is following the steps of simplex method, except instead of working with the previous tabular, we will work with the originals that we identify. And what do I mean by we will work with the originals that we identify will be clear as you perform those steps. Our first step will be to convert the given problem into our standard form. And here are the steps. Define the objective functions. It is maximize. It is going to be maximize. Now our constraints, for the first constraint we will have to add a slack variable s1. For second constraint we'll have to add a slack variable s2. For the third constraint we'll have to add a slack variable s3. So our constraints become what you see on the right side of the screen. And of course x1, x2, s1, s2, s3 are all greater than equal to 0. Now what we will do is, first step is, just like in simplex method we converted it to a tabular, in this case we will convert our problem into a matrix form. I am going to define a new matrix, and the matrix will have the coefficients of x1, x2, s1, s2, s3, which are the variables in my constraints, If I take those coefficients and populate the matrix, it will look something like this. So I have, from first constraint, I have 10 as the coefficient of x1. From second constraint, it is 6. From third, it is 4.5. x2 in first constraint is 5. In second constraint is 6. In third constraint, it is 18. The coefficient of S1 is 1 in constraint 1 and 0 otherwise. Coefficient of S2 is 1 in constraint 2 and 0 otherwise. Coefficient of S3 is 1 in constraint 3 and 0 otherwise. Next, what we do is we define a naming convention that our first column, which in this case is representing the variable x1, is called as P1. The second column is P2. The third column is P3. The fourth column is P4. The fifth column is P5. And if we had more, it would go so on. The next step is we will define XB, or the right hand side matrix, and in this case the matrix has value 50, 36 and 81 corresponding to 50, 36 and 81 in the constraints. And finally we define objective row matrix Z is -9, -7, 0, 0, 0, because the coefficient of x1 in our objective function is -9, coefficient of x2 is -7, coefficient of s1 is 0, coefficient of s2 is 0, and coefficient of s3 is 0. These are the two core formulas that we will be using for our revised simplex method. So consider that Pn prime is given by B inverse multiplied by Pn, and where the new value of a column vector Pn prime, so if we are working with P1, then the new value of P1, which will be represented by P1 prime, is given by the multiplication of inverse of the original column of basic variables and the original value of the column vector. Again, at this point I would say just consider that we will be using this formula or this equation to calculate it, and as we use it, it will get much more clear to you. Now we look at how do we identify the entering variable, and that is given by the equation Cn prime is equal to Cn minus Cb multiplied by Pn prime, and here the new value of coefficient of objective row is given by the original value of coefficients of objective row minus Cb multiplied by the Pn prime, which is the original value of coefficients of basic variables of objective row. You may want to notice is that in both of these equations, the right hand side of the equations are calculated from the original values, and what I mean by the original values is the matrices that we defined on the previous slide. So here are the original matrices that we defined on one slide prior to the previous one. In step 2, we already know which one of these variables are our basic variables. Of course, they are S1, S2 and S3. So our basic variables are S1, S2 and S3. The steps that are involved, the first step is we have to calculate the new Pn prime for non-basic variables. So what are non-basic variables in this case? They are P1 and P2, because P3 corresponds to S1, P4 corresponds to S2 and P5 corresponds to S3. So we will actually calculate P1 prime, which will be given by B inverse multiplied by P1, and P2 prime, which will be given by B inverse multiplied by P2, and we will also calculate the value of XB primes. In this equation, we know what is P1 because P1 is given by 10, 6 and 4.5. But what we need to find is what is B inverse. B is the basic variables matrix. In this case, our basic variables are S1, S2 and S3. So the matrix that we have for B is given by the values that we have in the columns of the basic variables. So B is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, And as I said, that the inverse of an identity matrix is the matrix itself. So in this case, B inverse is equal to B. So now for our first formula, we can easily calculate P1 prime. P1 prime, that means equals to the multiplication of B inverse multiplied by P1, and P1 is 1064.5. 1064.5, and if you do the calculation, you will see that the answer is 1064.5. You can use a online calculator for multiplying matrices for problems like this, or you can use R to do that. In your notes, there is a link to the online calculator that you can use, or I have a link to the how do you use R to calculate a product of two matrices. P2 prime similarly will be 5, 6 and 18, and we will calculate XB prime. So in the previous slide we had calculated P1 prime, we calculated P2 prime here, and XB prime. Now we will calculate the new coefficients of non-basic variables using the formula that was second listed on the formula sheet. So we have Cn prime is equal to Cn minus Cb multiplied by Pn prime. So we need to know what is Cb. Cb for our basic variables is given by the matrix of from the objective function corresponding to S1, S2 and S3. So in this case it's 0, 0 and 0. Since we are going to calculate C1 prime, we need to find what is C1, and C1 is equal to minus 9 because it is corresponding to P1. So C1 prime in this case becomes minus 9 minus product of matrix 0, 0, 0 to 10, 6, 4.5, which is 10, 6, 4.5 from P1. And what we will find is that C1 prime calculates to minus 9. Similarly, C2 prime calculates to minus 7. Similar to our simplex method with using Tableau, where we used to identify if there is still a negative value in our optimal row calculation, we calculated C1 and C2 for non-basic variables, and if any one of those is negative, we pick up the most negative one, and in this case the most negative is minus 9. That means C1 prime is the smallest negative, and hence x1 is the new entering variable. The method of identifying the exiting variable will be the same as what we have used in the Tableau method of simplex, where we calculate the ratio of the right hand side value to the selected pivot column. In this case we will find the ratio of the prime of xb to prime of the selected column of new entering variable, which in this case is P1 prime. So our right hand side calculation for ratios becomes 50 divided by 10, because 50 from xb prime and 10 from P1 prime. Similarly 36 divided by 6 and 81 divided by 4.5, which gives us 5, 6 and 18, and we will select the smallest positive, which is 5. Hence our corresponding leaving variable is S1, and we found that x1 is the new basic variable. We will now repeat steps 2, 3 and 4. And point to notice is that we again start with our original or initial matrix. So we have the original matrix, we have original xb, we have original z. However, the basic variables have changed to x1, s2 and s3. So we will calculate the new pn's for non-basic variables, which in this case will be p2 and p3, because x1 is basic, S2 is basic, S3 is basic. That means P2 and P3 are non-basic, and our formulas are P2 prime is equal to B inverse multiplied by P2, and P3 prime equals B inverse multiplied by P3, and we will find XB prime. Now since x1, s2, s3 are basic, our new value of the matrix B will be based on x1 column 1064.5 and S2 and S3 column to 010, 001. Again we will calculate B inverse you can use a online calculator or R to do that, and thus the calculation for our P2 prime is given by B inverse multiplied by P2, which is 5, 6 and 18, and the answer you get is 0.5, 3 and 15.75. We will now calculate P3 prime. P3 prime and P3 prime is given by B inverse multiplied by P3. We get 0.1 minus 0.6 minus 0.45, and similarly we calculate XB prime, which is B inverse multiplied by XB, the original right hand side matrix, and the answer is 5658. So just to bring the value of P2 prime from the previous screen, I have it here. Next, we calculate the new coefficient of non-basic variables. So in this case, x1, s2 and s3 are our basic variables. So CB is given by minus 9, 0 and 0, and we know that C2 is equal to minus 7. So C2 prime is equal to minus 7 minus CB, which is minus 900 multiplied by P2 prime, which is 0.53, 15.75, and the answer that you get is minus 2.5. Similarly, C3 prime will be 0.9. Now clearly, for our interest, we are looking at anything that is a negative number, and C2 prime is the smallest negative, and hence x2 is the new entering variable. Again, we calculate the ratios using P2 prime and XB because P2 prime is the new entering variable or equivalent to our pivot column in standard simplex method. We had calculated XB prime as 5658, so our ratio becomes 5 divided by 0.5, 6 divided by 3, and 58 divided by 15.75. Your answers are shown here, and which means we have to find out the smallest positive, which is 2, and it points to S2. So the leaving variable is S2, and we had found that X2 is the new basic variable. Again, we will repeat step 2, 3 and 4. Our original matrix are still the same. However, we have now basic variables x1, x2 and s3. So we have to calculate Pn primes for non-basic variables, which in this case will be P3 and P4, which means our B matrix is given by the 10, 5, 6, 6, 4.5, 18 and 0, 0, 1. Once we find the B inverse, it is given by the values that you see on this part of the screen. Thus, P4 prime from this formula is given by B inverse multiplied by P4. P4 is 0, 1, 0, 0, 1, 0. It becomes minus 0.167, 0.33 and 5.25 with a negative sign. Similarly, we calculate P3 prime, which is B inverse multiplied by P3, and then XB prime, which is B inverse multiplied by XB. We get this value, and we had calculated P4 prime previously, this value. Now we calculate the new coefficients, and we know that CB is given by x1, x2 and s3 in the objective row, which is minus 9, minus 7 and 0. So if we want to calculate C4 prime, we know that C4, which is 0, from here, substituting the values of CB and C4 in this equation, we can find C4 prime. C4 prime comes to be 0.828, and similarly C3 prime comes to be 0.4. None of the two C's are negative, which means we have reached an optimal solution, and we get x1 equal to 3.98, which is rounded to 4, and x2 is equal to 1.98, which is rounded to 2. So to wrap up, the revised simplex algorithm looks similar to the tabular method, except the only difference is that for each cycle or each iteration, we will always start with the original matrices, identifying the P matrix dependent on the basic variables, and then finding the P prime values for non-basic variables. And then we find the value of XB prime and we select the pivot column from the most negative value of pn's of non-basics, and we identify the exiting row or exiting variable using the ratio of xb prime to the selected pn prime. And this method goes on until we have no new basic variables, which means all the values of the cn's primes are positive.